Okay, so we'll start now. So, good morning and welcome to this lecture. And it's really nice to be back in the classroom after a gap of 2 years. And it's also a new topic after the topics covered by Professor Ghosh. So, today we'll talk about transactions. So, effectively, to give you an idea about the rest of this semester's plan, we are planning to cover topics from chapters 14, 15, and 16, and just a couple of topics from chapter 12. And all these chapters, PPTs, these are uploaded in our MS Teams in this particular courses page. So let us start with transactions. So this is something interesting. So we'll talk about concept of transaction state, what is meant by concurrent executions, serializability of what is called a schedule. We'll study about that, recoverability, implementation of isolation, what this concept is, and then transaction definition in SQL, and then testing for serialization. So transaction concept. So let us start with that. And those who are joining online, they may please, I may not be able to see your hands raised, so you may simply ask your question. That is no problem. Okay, good. So, formally we define a transaction as a unit of program execution that accesses and possibly updates various items. So let us take a look at one example. So suppose we want in a database application, we want to transfer some amount of money. So here we talk about say $50 from account A to account B. So what we have to do, so there must be some initial balance in account A. Presumably that will be more than $50 unless there is overdraft or something. So let us assume that in account A, the balance is more than 50 and account B has some balance, and we are transferring $50 from A to B. So what we do is, we of course first read A, say the initial balance of A was 1000 and initial balance of B was 2000. So we see what is, because there is only one person, I think I remove my mask. You keep wearing the mask. Okay. So, and so we read A, so A was 1000, and then we are transferring 50 from A. So A's balance will be, or the value of A, which is the balance itself, will be reduced by 50. So A is A minus 50. We write A, so we write 950 in A, and then read B, which is 2000, and then B we make it 2050, and then write that value of B back in the database. So this is what is meant by a transaction. Means a unit of work or unit of program execution as mentioned here. And there are a few things that we'll see which are important. And very first definition is that this type of unit of program is what we denote as a transaction. And we have so many of these examples actually happening in practice, which you have yourself seen. Also in our discussions previously, we have mentioned about this. So let us consider that I update your grades at the end of the semester. So what I have to do is that I have to update your grade maybe in one table, which is similar to the registration table we have discussed so many times in the context of PR diagrams and our database design and so on. The value of your grade for a particular course. But the transaction includes some more tasks. So that is one task, is to insert a row in the registration table, which will have, or maybe go and update the value of grade in the registration table if it already has this row, which is course code, say DBMS, and then we have say your roll number, course code, and then the value of grade is what I will be updating. Okay, so that row already is there, and I update your grade. You please keep wearing the mask, then I can remove it. Okay, otherwise I have to add an. Okay, so then what it means is that we have to update the value of grade in that table for a particular row. But also what we need is that I have to go and update. I have to means that the system, the database management system, as part of the same transaction, will have to go and update the value of CGPA in another table, which might be say the student table, which has your roll number, name, department, and maybe the current CGPA. So this is another example. So every time that we have talked about databases and applications, we actually have talked about these transactions. Now we'll see that there are a few issues with this. So the two main issues is that failure of various kinds, such as hardware failure and system crashes, we should be able to handle it. And very importantly, that there could be other transactions also which are getting executed concurrently, meaning that part of some of those instructions of other transactions are also getting executed concurrently with the instructions of my transactions. For example, one other professor is also going and updating the, say, the registration table with the value of grade for another course, and that itself also will have to go and update the value of CGPA. So while my updating of the grade for DBMS course is going to update the value of CGPA in another table, similarly somebody who is entering, say, value of grade for your networks course, so that transaction also will have to go and update the value of CGPA. So this is what we mean by concurrent execution. So before my transaction is completed, another transaction started, and their instructions are interlinked. So we have to think about that. So what are the properties of transaction? So we define these properties as, in short, colloquially we call these as atomicity, then consistency, isolation, and durability. So we call them as ACID. So we'll talk about all these properties. So as you see that we have put them in a different order, which is the order in which it is easy for you to understand. But the first letters of these properties of transactions, they are like ACID, and we in colloquial terms call this as ACID properties. Okay. Now, what is atomicity requirement? So it's very simple that if the transaction fails in this example after, say, step 3 and before step 6, money will be lost because from A we have reduced the 50, but we have not updated the value of B. So you see those $50 that we talked about, that got lost. So we cannot allow that. So that is what is called the atomicity requirement. Means either all of these instructions of this transaction will get executed, for that matter for any transaction, all of the instructions will get executed and complete and be successful, or if there is some issue in between, then it should be such that the effect will be that all the small steps that were taken, those are all reverted back. So either all the instructions will complete, or there will not be effect of any one of those instructions. So that is what is meant by the atomicity property. The other is that the durability is that once the user has been notified that the transaction has completed, suppose about this, that it is A's account holder is going to do this transaction of transferring 50 from his or her own account, which is A, to somebody else's account B. So after the transfer takes place, with all these 6 instructions are completed, then of course this account holder will get a message that $50 successfully transferred to B. And once that is done, the point is that the durability property requires that after that, if the system crashes, and what is meant by system crash, we'll talk about that. So once the system crashes, or if the system crashes, so then also it should not be a case that then those $50 history is lost, or the user will have to again carry out that same transaction. Okay, so that is what is meant by durability. Of course, in between, if it crashes, then by that time the user has not got the message that the same transaction, and which we often see, right? We see, say, while paying our tuition fee through ERP, so it takes me to a payment gateway where I make the payment, it says successful, but then it is not able to come back sometimes. Usually it comes back most of the times, but sometimes it does not come back, and then it does not immediately get reflected in your passbook in ERP, right? But you will see that the message normally is that after some time it gets reconciled and it gets updated. There are again rare cases where even after some time it does not get executed, but then there is a process of ensuring that reversal of transaction takes place. So there is a manual intervention. We'll discuss about that later. So that is a different type of transaction. But normally, like if for example I update your grade and it says that grade successfully updated, CGPA recomputed and all that, after that, it should not be a case that I will be told that, oh, hold on, that something went wrong, now you have to again enter the transaction. So that property which ensures that once everything has been updated properly and I get a message typically, then this durability property or the durability requirement means that I don't have to do it again. The consistency is something a little tricky, is that what we did here, you see that say the account holder says, oh, transfer $50 from my account A to B's account. Okay. Now, so the underlying code should actually transfer. So it is not always $50, right? Some amount X. So it should deduct that X from the source account and then add that X to the destination account, right? Now, if in between, instead of writing say equal to A minus X and B equal to B plus X, the programmer has written A equal to A minus X and B equal to B plus 2X, then the database cannot do anything about it. And that is what is called consistency. So that means that this property that the transactions will lead the database from one consistent state to another consistent state. That is what is called the property of consistency of transactions, but it is usually the onus is on the programmer to ensure that the consistency is maintained. So you might wonder, so it is all with the programmer. So what's the big deal? Why the database management system people would be bothered? Okay. The reason is that certain things like this X equal to X minus or A equal to A minus X and B equal to B plus 2X. I said that it can be carried out and the database cannot do anything about it, but it is not always the case, so I will come to that. But database actually provides a lot of facilities to help the programmer maintain consistency. For example, say you know about these foreign keys and differential integrity and all. What it means? It means that suppose in the student table, I want to insert a row where I will put roll number, name, and a department code, but the department code I put some XY and there is no department with the code XY, so that is going to make the database inconsistent. Okay. So in order to ensure consistency, so even if the programmers write it, how does the database ensure that still the database is consistent and no inconsistent data is allowed? If we have properly defined the foreign key, then that department code XY, if it is a valid code, then that must already exist in the department table, that XY and the name of the department is so and so, right? If not, then because of the foreign key failure, the database will not allow me to carry out this inconsistent transaction where I am trying to enter a department code of XY for a particular student, right? So that is the whole point, that although it is the onus is on the programmer, but database provides certain facilities like primary key. You cannot enter the same roll number twice. So that is another example. You have a check constraint that these values can only be say spring, autumn, and summer, right? So these are the possible values for your semester. So even in this example, that if the programmer wrote A equal to A minus X and B equal to B plus 2X, but if we have a constant that the sum of the balances always will be equal to the same value even after these types of transaction, then of course that B equal to B plus 2X also will not be allowed by the database, right? So the point here that we are trying to make is that this requirement is something where the onus is more on the programmer or mostly on the programmer. The database provides only certain facilities to ensure that consistency is maintained under most of the situations. But the previous two, atomicity, durability, and the next one, isolation, So these are the properties of the transactions which are actually guaranteed or are meant to be guaranteed by the database management system itself. And now I will link it back to our discussion in some of the first few lectures, that why we are having the database management system and not using, say, the files. Okay, is that having all these properties for every programmer to implement for his or her own database application will be cumbersome. Okay, and it may not be correct. So the database management system itself provides this facility, so that when the programmer writes a database program or builds a database application, the programmer did not worry about that. The database itself or the database management system itself will take care of it. And if you consider the types of mini projects that you have developed, you never even thought that there is something called atomicity, something called durability, and I'm coming to what isolation is. Because the underlying database management system is doing it. Even if you carry out those transactions concurrently, transaction, you shut down your machine, you will see that it will still be able to maintain this atomicity property. Or if after your whatever updates are committed, you get a message that this is successfully updated, then even if that, if you shut down your machine and restart, you will see that the data is already there. Isolation is something which is a little tricky. So if you see this, that say I have two transactions T1 and T2 getting executed concurrently. So I have, say, T1 having done the first three instructions, like which you have seen, reading A equal to minus 15 and writing A. And then before T1 has read B and updated B by that 50 and write B, so there will be the closing parenthesis. So T2, what it did was T2 read A, B and printed A plus B. So what will happen, you see that this value of B that T2 is reading is the original value of B, that is, say, 2000, but the value of A that it read is 950, which is after reduction by 50. So what it will print 2950 as the output of printed plus B. But actually, this is not correct, because only the part of T1 has been executed, and then T2 read both A and B and printed A plus B. Okay. So, but you see that if T2 printed it before the first instruction of T1, then also it will print 3000, 2000 plus 1000. And if T2 printed this A plus B after reading A and B after the sixth instruction of T1, then also it will get this 950 plus 2050, it will get 3000. So it will get it will get printed correctly. Okay. So the point is that if we allow this concurrent execution in any such arbitrary order without any control, then we will get something which is not expected, and this is not a correct output. So what is important is that we have to ensure that even the concurrent transactions will be executed, only certain types of intermingling of these individual instructions of the transactions should be allowed by the database management system, so that the output that we get are actually correct. Okay? So this property is what is called isolation. Now, why is it called isolation? It means that the property of isolation guarantees that even if the transactions are executed concurrently, they get executed in such a way that it gives an impression as if the transactions are getting executed in isolation. So that is why it is called the property of isolation. So actually there will be concurrent operation. Of course, not every types of, as I said, intermingling will be allowed. Only certain types of intermingling which will maintain the property of isolation, and the property of isolation means that the output that we will get will be same output as what you would get had the instructions been executed in isolation. So that is why this property is called isolation. Okay? So of course, that trivially what you can do is that trivially, if you always allow transactions to be executed serially, then that isolation is trivially guaranteed. But that makes no sense, because we know that concurrent support for program execution is indeed important for various reasons, like the average waiting time and all those things. We study those concepts in operating systems. So what we will do is that we will is mostly dedicated to, though in this chapter we'll also talk about it, is that what types of this intermingling of instructions of various transactions? It will not be only two, right? There will be maybe hundreds of transactions going on. So how we can ensure, and by we I mean the database management system can ensure that in spite of concurrent execution, that isolation property is maintained. So that is what is something that we have to see. So this is, as I said, that these are the basic properties: atomicity, consistency, isolation, and durability. And of course, we know about concurrent execution. There are indeed benefits. We are not going to go into that. We know that if there is a small task and it is unnecessarily waiting behind a lot of long tasks, the average response time is going to increase, and if you allow concurrency, then you get overall better response time. So, but how do we ensure that this concurrent execution of transactions, ensuring the property of isolation, it is to also ensure the property of atomicity, the property of durability. So all these properties will be ensured, okay, and indeed at the same time will allow concurrent execution. So these are what are called concurrency control schemes, which we'll study in chapter 15 in detail. But here we'll talk actually about the concept of what is meant by these concurrent executions and what we call as a schedule. So we'll try to understand what is meant by a schedule. So a schedule is this term is important. It's a sequence of transactions that specify the chronological order in which instructions of concurrent transactions are executed. So a schedule basically is a set of transactions to start with, and it also shows that in which order, in time order, by order I mean the temporal order or chronological order, the various instructions of each transaction get executed. So that is what I am saying, how they are intermingled. So if there are two transactions T1 and T2, then we have various different ways, all sorts of permutations of their instructions effectively will tell us that what are the different types of schedules you can do. Even with two transactions T1 and T2, if T1 has 3 instructions and T2 has 2 instructions, so you see that these 3 and 2, these 5 instructions can be intermingled in so many different ways, and each giving rise to a different possible schedule. So let us see that what is meant by a schedule. So there are two other terms. The transaction that successfully completes its execution is going to have a commit instruction as last statement, and if the commit instruction gets executed correctly, then you get the message that, oh, your transaction is successful. So if you consider again your ERP application, suppose you click on, you choose your subjects to register, and then you say that, okay, submit, and then it asks you, are you really sure, and then again, are you really sure, and all that, and after that when you click yes, and it says that this your registration has been successfully saved. So that means that the end of the transaction will have what is called a commit statement. Okay. And for some reason, if this transaction comes out, then it will have an abort instruction. So abort instructions, of course, you will not put on your own. But if for some reason, like I'll just quickly give you one example here. Say the transaction started with reading A, it reduced A by 50, writing A, then it reads B, and then it finds that there is no account called T. Okay? It does not know beforehand, right, that there is nothing called T. So what it does is that it keeps doing the first 3 instructions, and then when it goes to the 4th instruction, read B, it finds that there is nothing called T, and then what it has to do, it has to abort. Okay, so or often we call as rollback. Okay, so that is why we have to ensure that the effects of the first 3 transactions, that is reducing A by 50, those are reversed, so that A will go back to its original state, which was 1000, and B was not there at all, so there is no issue. So it will, the database which was consistent before this transaction got started, so that was consistent, and after abort also it is consistent. If indeed B was there and B's value could be increased by 50, then A became 950, became 2050, and that also again a consistent state of the database. Okay, so it is important that we move from one consistent state of the database to another consistent state while we are executing such schedule of transactions. So transactions will keep coming, getting executed, getting completed, through commit, or they get aborted, and accordingly the data will either be committed to the database and it becomes durable, or it becomes aborted and then you roll back everything, but still the database gets committed. But you see that there will be no manual intervention, and there is nothing like stopping the transactions for coming in just because one transaction was aborted. So the transactions, millions of these transactions will keep coming in and they will get executed, and the DBMS will ensure all these four properties. So that is what is meant by its commit and abort. Now let us take a look at our particular schedule. So what is meant by schedule? So as I said that it is a collection of transactions. We have two transactions T1 and T2 here, and then T1 reads these things, and like as you can see, it moves 50 from A to B, and T2 what it does is that it computes 0.1. So fixed percentage, 10% of A is reduced, so is reduced by 10% of itself, and then B is increased by the 10% of A. So if we consider that initially, say I had 1000 and 2000 before these two transactions came in A and B. So what T1 does, T1 moves 50, so A becomes 950, B becomes 2050. And then what T2 does, it takes out 10% of 950, which is 95, okay, and that it adds to B. So 95 is reduced from A, so it becomes 855, okay, and B already had 2050, and then it gets that additional 95, so it becomes 2145. Okay, so that is the whole concept. Now this is a schedule where I have shown transactions T1 and T2 in terms of all their instructions, and also we have shown the chronological order, meaning here you see that T2's read date occurs after the commit of T1. Okay, so we have shown them one after the other. So all the instructions, so the first instruction of T2 starts after the last instruction of T1. So this is, as you can see, is called a serial schedule. Here T1 is followed by T2, means all instructions of T1 get executed, then only T2 starts executing. So this is an example of a serial schedule. Now the same set of transactions T1 and T2, they form now schedule 2. You see it is written as schedule 2, previously it was schedule 1 in the title. So schedule 2 is what? It is the same set of transactions, it is the same set of instructions, it is a serial schedule, but now what has happened? Now we have these instructions of T2 getting executed first, and then T1 starts executing. So this is again an example of a serial schedule where T2 is starting first followed by T1. But you see in this case, even if we start with say 1000 and 2000, of course at the end of execution of T2 and T1, we'll get different balances in A and B, which is pretty obvious. But this is also consistent because you do not know that whether T1 will come first or T2 will come first. So it so happened that in the database management system, that transaction which is removing 10% from A and putting that in B, that transaction came in first, it got executed, and then this transaction T1 came and it got executed. So even if we start with 1000 and 2000, we'll end up with some balances in A and B, which is not the same as the previous balance, but that is also consistent because there is nobody to tell that this is always supposed to come first. So they will come in any order, but we are only talking about serial schedule, where one comes before the other, completes, one comes before the other, completes, then the next one comes. And if we had more number of such transactions, not only two, and if all instructions of say T2 first get completed, then all instructions of T3 get completed, then all instructions of T1 get completed, and then all instructions of T4 get completed, and so on. So these are all examples of serial schedule. Now take a look at this schedule 3, which is now a concurrent schedule, because we have some instructions of T2 happening in an intermingled manner with the instructions of T1. So what we see here is that we have this T1 first reads A and A minus 50, and this T2, what it does is that it and wrote back the value of A, and then what we do is that we T2, it reads the value of A. So if it was 1000, so T2 now reads that 950, and then it again computes 95, and then we have read B, so which is reading 2000, and then it is incrementing D by 2050, and then this D is further incremented by that 95. So you see that in this example, what has happened? This is a different schedule. We call it as schedule 3. It is a concurrent schedule of the same transactions with the same instructions. But you see that we have allowed concurrency. Okay. And what has happened? Even with that, you see that the sum of A plus B is preserved. Okay. So if we see here that we have an example of serial schedule, then a second example of a serial schedule, and now this third schedule is a concurrent schedule. But what is the net impact of this? Net impact of this is whatever the values of A and B you get after completion of this schedule, that is both the transactions T1 and T2, the values of A and B that you get, which is the database state at the end of this schedule 3, is the same as the state that you would have obtained at the end of schedule 1, not the same as the state you would have obtained at the end of schedule 2. Okay, so that means what? That means that this is a concurrent schedule, but it is equivalent to schedule 1, which is a serial schedule. So that means the schedule 3 is equivalent to a serial schedule. So when a concurrent schedule like this is seen to be equivalent to some serial schedule, not necessarily all possible serial schedules, which is usually not possible, but if it is equivalent to at least one serial schedule, we call such a concurrent schedule as a serializable schedule. Okay? So this schedule 3 is called a serializable schedule because it is equivalent. Currently we are putting equivalent in blue, so it is quote unquote equivalent. So what is meant by equivalent, or we have to define what equivalent is, that will come to. But we see that in some sense that the A and B, the sum is preserved. So that is guaranteed by schedule 3, and its net impact is equivalent to the net impact of schedule 1. Schedule 1 is a serial schedule, so this schedule 3 is equivalent to a serial schedule. Hence, we call this serial, this concurrent schedule, schedule 3, in this case as a conflict serializable schedule. But what is meant by, or initially it is called as a serializable schedule. What are the types of serializability? I am coming to very soon. So, is there any question up to this? Anyone who is also attending online? Okay, so Vanshit, I don't know if you're asking anything, you are muted. So, if there is a question, you may unmute. Otherwise, let us proceed. Okay, now if you look at this one, again, this is the same set of transactions with the same set of instructions, but the only difference you see that T2 is reading the value of A before that A was written back. Okay, in contrast to the previous example. So here for T2's read A occurred after write A of T1, but here we see that T2's read A occurred before the write A of T1. And you can easily see that this value of A that was written by T2, that got overwritten by the value of A that was determined by T1. So although T2 computed this 10% over 950, so what it did was that the 95 it deducted and wrote back, but now A is writing, so A will write back 950. So instead of that additional 10% being deducted from A, what we have is that this 950 got written back to A. So as you can obviously see that this does not preserve the sum A plus B. So this is not a schedule you would like to have, because why? Because it violates the property of isolation. Why? Because if the transactions indeed were executed in isolation, means they were basically executed serially in one of these orders, T1 followed by T2 or T2 followed by T1, or if there are more transactions, T1, T2, T3 or T2, T3, T1 and T1, T3, all possible permutations. So if it was equivalent to any one of them, it was okay with us. But if not, if we allow this type of concurrent execution of schedules or concurrent execution of transactions forming such a schedule 4, then this does not preserve the property of isolation of transaction, because if these transactions indeed were executed in isolation, that is not concurrently, they first were executed T1, then T2 or T2 then T1, you will never end up getting the values of A and B that you would get if you allow such a schedule to be formed. So what we see here is that we have seen that for concurrent schedules, certain types of concurrent schedules we can allow, but certain other types of concurrent schedules we should not allow because they will result in violation of the property of isolation. Okay, is that clear? Okay, good. So now we have to understand a little bit more about the formalism, and then let us see how we can ensure that such schedules do not get formed, or what allows such schedules to be formed, and we should not let that happen. So that is the whole point. Okay, so serializability. So now we come to the actual definition of serializability. The basic assumption is that each transaction preserves database consistency. Consistency is important. That means before the transaction started, the database was in a consistent state. Now the transaction getting executed potentially concurrently with other transactions. But even after that, when the transaction completes, the database should not reach an inconsistent state. So that is the whole. So trivially, as you can see, that serial execution of a set of transactions preserves consistency. But now, concurrent schedule is serializable if it is equivalent to a serial schedule, which I have already mentioned. And so a schedule that is serializable, that is equivalent to a serial schedule. And serial schedules are always going to ensure consistency. So if we end up only forming serializable schedules, the database management system enforces the property that only serializable schedules will get formed. Then also what we can say is that even though concurrent executions are happening or concurrent schedules are getting formed, still the database will be consistent and we are to also have the property of isolation. Now there are two notions of serializability. One is what is called conflict serializability and the other is what is called view serializability. So, for understanding that, what we do is that we simplify the views of transactions. So, we ignore operations other than read and write. So, whether this is doing a minus 50 or a minus 20 or a minus 100, they will not matter. We will only focus on this read A and write A. So, in terms of that, we will be able to simplify. So, that is what we can only have, say, for two instructions II and IJ of two transactions PI and PJ. Okay, so say II and IJ will say that. So II is an instruction. So instruction is like this: read A, write A, those ones. Okay, not the actual changes because they don't matter, as I said. So each of these read A, write A, these are each of these instructions. So suppose I have transaction PI and it has got an instruction II, another transaction PJ with an instruction IJ. So these two instructions I and IJ conflict if and only if there exists some item Q accessed by both I and J and at least one of these instructions wrote Q. Why? So first of all, if II is doing anything on P and IJ is doing something else on Q, they never conflict, right? II is changing P or reading P, IJ is changing Q or reading Q, there is no conflict at all. So you can always mix them in any order. Now, if both II and IJ, they read the same data item Q, then also there is no conflict. If the value of Q is 100, II will also read 100, IJ also will read 100, there is no issue. And whether II occurs first and reads Q and gets 100, there is no problem. Similarly, if IJ first reads Q 100 and then II reads Q as 100, there is no problem. Problem comes if one of these II and IJ is a right operation, because then we have a conflict. Why? Because let us take the value of Q is 100. Okay. Now, if II is read Q and IJ is write Q, okay, then if II comes first, then II will read which value of Q? The original value of Q, not the one that has been written by IJ. Okay. But if it is the other way, if IJ comes first and then II comes next, then IJ is the right Q. So IJ has written the new value of Q and then II is reading the new value of Q. You see that then the value that will be read by this II will be different. It will depend on whether IIQ came first and then IJQ, where IIQ is read Q and ijq is write queue, or ijq came first, which wrote the value of q, which was later read by ii as read queue. Are you able to follow that? So you see that these two instructions, there is a conflict in terms of the net effect they will have based on which one comes first, which one comes next. Okay. So of course you can treat ii doing a write queue and ij doing a read queue, it will be the same symmetrical. And if it is both a write queue, then if ii comes first and writes q and then ij writes q, then what will remain in the database? The value of q that has been written by ij. The value of q written by ii will be overwritten. Okay, so that will result in a different database state. And instead, if ijq came first and then iiq and both are write q, then ijq will first write q and then iiq will write q, and it will overwrite what was written by ij with the value of q. So you see that the net effect will be different from if iiq came first and then ijq. So what it means is that this is what we call these instructions conflict. Means we cannot allow them to order in any one of these orders and then still end up getting the same database state. That will not happen. Okay? So intuitively, a conflict between I and ij forces a logical temporal ordering between them. So if we say that I am going to follow this ii followed by ij, okay, then if we do it the other way, then there will be a conflict. If at least one of them is a write operation and both of them are writing to keep. Okay. So conflict serialization. Now this definition is important. So if a schedule can be transformed, a schedule S, so presumably S is a concurrent schedule. If a schedule S can be transformed into a schedule S prime by a series of swaps of non-conflicting instructions, because as I said that if read q and read q are there as ii and ij, so swapping means I can do read q first and then of ii first and then read q of ij. Temporal order. That is what we mean by that swapping of non-conflicting instructions. We say that S and S prime are conflict equivalent. So I have a schedule S, I have a schedule S prime. We are not saying whether S or S prime are serial schedule or concurrent schedule, but by swapping these non-conflicting instructions, if we can convert or transform S into S prime, then we say that S and S prime are conflict equivalent. And we say that schedule S is conflict serializable if it is conflict equivalent to a serial schedule. That means that if S and S prime are two schedules and S is conflict equivalent to S prime and S prime is a serial schedule, then S is a conflict serializable schedule. So again I am repeating this, that you can have two schedules S and S prime, both are concurrent and they may or may not be conflict equivalent to each other. But if S and S prime are such that S is conflict equivalent to S prime, then S prime is a serial schedule, then we say S is a conflict serializable schedule. Suppose S is a serial schedule, so it is conflict equivalent to itself, which is a serial schedule. Hence, trivially, any serial schedule is conflict serializable. But of course, a serial schedule is a more harder concept. So, but again remember that if S is made up of T1 and T2 and S prime is made up T1 and T2, but S is T1 followed by T2 in serial sequence and S prime is T2 followed by T1 in serial sequence, then S is not necessarily equivalent to S prime. So it is not necessarily that two serial schedules made up of the same set of transactions will be equivalent to each other, like conflict equivalent to each other. That did not happen, as we have seen before. Okay, that depending on those which one comes first, which one comes next, we can have different final state of the code. So they are not conflict equivalent, but each of them trivially is conflict serializable because they are serial schedule in the first place. So let us see some example. So if you see that schedule 3, if you remember we had that schedule 3, I am just referring it back once for your convenience. This is schedule 3 and we have removed everything other than the read and write. Okay. So if you look at now this example, that schedule 3 was this read A, write A, read A, write A, then read B, write B, read B, write B. Now you see that T2's read A, write A, they are operating on A and T1's read B, write B are operating on B. So you see that I can break down this read A and write A below read B and write B. That is what we are saying by this swapping. Okay, that they are ordering, we are swapping, and then what we get, we move read B write B up and move write A read A write A of T2 down, and we get a schedule. And you see that this is conflict equivalent. Schedule 3 is conflict equivalent schedule 6. Why? Because by moving the non-conflicting instructions of this, I am able to transform the schedule 3 to schedule 6. Okay. And what we see, what is schedule 6? It is a serial schedule. So schedule 3 is conflict equivalent to schedule 6, and schedule 6 is a serial schedule. Hence, schedule 3 is a conflict serial execution. Okay. Also, what is important that never do this, that you cannot change the relative ordering of the instructions within each transaction. I cannot move read B of T1 before write A of T1. That is not allowed, because that is how you have written your transaction. And just to help you understand a little bit more, transaction is simply that if you have, say, in those mini projects that you have done, that you have select start from one table, if you do something, then update another table or insert. So they all are happening in the context of a transaction. So that is essentially a transaction. So, like we said that you read the value of A, so you will select, say, whatever is the column name, say balance, account balance, where account number is. Okay. Then you will say update account, set balance equal to balance minus X, which might be 50, where account number is A. That is what you equivalent SQL operations or SQL statements. Okay. So that is all we are talking about. So then if you have written the code in a particular order, then that you cannot change by execution. DBMS cannot change that. So that means you cannot move read B before or before write A or read A T1. Okay. But what we are saying here is that if I consider schedule 3, which is a concurrent schedule, and if I can move these instructions a little bit down of T2's read A write A below read B write B of T1, then they will not conflict, and the net effect of executing the concurrent schedule, schedule 3, starting from no matter whatever is the initial value of A and B, will be exactly the same as the execution of the serial schedule, schedule 6. Okay. So because of that, schedule 3 is a conflict serial execution. Is that clear? Now, if we look at this example, here it is not conflict serializable. This write Q, I cannot move before read Q, or write Q of T4, I cannot move before read Q of T3, because these are read and write and they conflict on the same data item. Write Q of T4, I cannot move below write Q of T3, because they will have this difficulty that they are conflicting. Okay, so this is an example that schedule which is not conflict serializable, because it is not conflict equivalent to any serial schedule. Now, how can we determine? So there could be many such transactions, right? That are happening. So, and how do you determine whether any schedule that is given to you is conflict serializable or not? Okay. So what we do is that we can create what is called a precedence graph and see if there is a cycle. So what we do is that each of these transactions that form a node of the graph. Okay. And then we'll draw an edge from T1 to T2, okay, under certain situations. When, if T1, this is very simple, if T1 does a read Q before T2 does a write Q, then I will draw an edge from T1 to T2. Or if T1 does a write Q before T2 does a read Q, then also I will draw an edge. Or T1 does a write Q before T2 does a write Q, I will draw the edge. So that means that if, again I am repeating, that T1 has a read Q instruction which is before a write Q instruction of T2, then the edge will be drawn. Or T1 has a write Q, T2 has a read Q, then also the edge will be drawn from T1 to T2. If T1 has a write Q, T2 has a write Q, then also the edge will be drawn from T1. And then conversely, that if T2 has a read Q before write Q of T1, then I will have an edge from T2 to T1. Or T2 has a write Q before T1's read Q, also I will draw an edge. Or T2 has a write Q and T1 has a read Q, then also I will draw an edge. Now, of course, this Q could be P, Q, R, X, Y, Z, whatever. Okay, and they could be reading many such. So it is possible that T1 does a read of P before T2 does a write of P, and T2 does a read of Q before T1 does a write of Q. Then because of P I will have an edge from T1 to T2, because of Q I will have an edge from T2 to Q. Okay. So we will have this. And then once you have the precedence graph, if that is a cycle, that means that there will be this conflicting ordering, that you cannot move all the instructions of this one up or all the instructions of this one up. Because of those conflicts, it will not let you do, and that gets captured in the precedence graph in the form of the existence of a cycle. Okay. So it is simple that schedule is conflict serial schedule even only if its precedence graph is acyclic. Okay. So like if you see the first example, that Ti, Tj, Tk, Tn, so we see that there is no cycle. Okay. So then the schedule for which the corresponding precedence graph is A, that will be conflict serializable. Okay. Now if it is conflict serializable, that means that it must be conflict equivalent to some serial schedule. Now with which serial schedule is it conflict equivalent? If you have T1, Pi, Tj, Tk, Tn, so 4 such transactions, so you see that there could be permutation of these 4, so factorial 4 number of possible serial schedules. Mind that this, just because this schedule, which is represented by its precedence graph in A, is conflict serializable, does not mean it will be conflict equivalent to all possible of those factorial 4 serial schedules. Okay. Now it will be equivalent to which one? It will be equivalent to only those schedules, those serial schedules, which you can get by topological sorting of this precedence graph. So that means that Ti has to be there first. After that, Tj or Tk, anything will be there, but Tn must be after Tj and Tk. That's what topological sorting means, right? So that means that this ordering of Tj and Tk is not important. So this topological sorting of this graph will be Ti, Tj, Tk, Tn or Ti, Tk, Tj, Tn. So the schedule represented by the precedence graph A is equivalent to a serial schedule which is Ti, Tj, Tk, Tn, and it is also equivalent to the serial schedule Ti, Tk, Tj, Tn. But it is not equivalent to the serial schedule say Ti, Tn, Tj, Tk or Tn, Ti, Tj, Tk, anything like that. Okay. So out of those factorial 4, only with these two it is conflict equivalent. Okay. So you see that you can test for conflict serializability in this manner. So and which is polynomial time algorithm as a result of this. So recoverable schedule. So this is another concept, that if a transaction Tj reads a data item previously written by a transaction Ti, then the commit of Ti must appear before the commit operation of Tj. Otherwise, what will happen? That Tj has read a data item written by Ti, suppose Tj commits. So Tj is done, it made some changes, etc. Now Ti says I will. So then whatever values Ti wrote, those will be set back. But Tj already has read those and it has committed and gone ahead. So then you cannot recover the things because it is all now messed up. Because what Ti changed, Tj read it, wrote something based on that, completed everything, went away. Okay. Now you say no, what Ti wrote, that was not correct, I cannot proceed, it has to be aborted. So it ends up in the schedule non-recoverable. Okay. So you see that Ta reads a, writes a, T9 does a read A, now say T9 commits and then T8 does read B and then T8 tries to abort. Then it will roll back whatever values was written by T8 for A, so it will go back to the original value of A. But T9 read the value that was written by T8 and then it went ahead and did something. Okay. So in between it might have printed something and told the user that, oh, this is your account balance or whatever. So this is something makes a schedule as non-recoverable. The other is what is called cascading rolling. Okay. So suppose we have this, that read A, read B, write A, then read A, write A, and then read A. So what we see here is that T10 reads something for A and writes to A. That value is read by T11. Okay, so suppose T10 wrote the value of A as 10, and then T11 read that as 11, and then suppose it increments by 1, makes it 12, and T12 reads 12. Now, if T10 aborts, what it will have to do is that it will also have to abort 11 because 11 did it wrongly. It will also have to abort 12 because it read a wrong value which was written by T11 based on what was written by T10 and so on. So it results in a cascading rollback. That lot of things will have to roll back. So what it means is that none of transactions has yet committed, so the schedule is recoverable, but it will be cascading. Okay, so we have these difficulties that we have to think of when we come up with the various schedules. A cascadeless schedules for each pair of transactions Ti and Tj, such that Tj reads the data item previously written by Ti. The commit operation of Ti appears before the read operation of Tj, so that Ti only reads committed values. Otherwise, if Tj aborts, it will also have to do a cascading, aborting or rollback. So every cascadeless schedule is also recoverable, which can be trivial issue because it is always going to do it after the previous one has come. So it is desirable to restrict the schedules to those that are cascades. Otherwise, there will be a lot of such unnecessarily this undoing of significant amount of work. So this is an example of a schedule that is not cascadeless, which is same as the one we had in the previous slide. Okay. So you would like to ensure having cascadeless schedules, and cascadeless schedules are also recoverable. That means that if you ensure the property of cascadeless, you will also be able to ensure the property of recoverability. And of course, you have to ensure that you are generating serializable schedule, like the conflict serializable schedules. But there is only the final one about this, which is called view serialization. Okay, so let me explain this. What it means. So certain things are written, but let me first take this example. Okay. So if you see this example, here we can obviously see that it is not conflict serializable. Why? Because this right Q of T28, neither you can move above T27 nor you can move below T27, right? So that means that T27 and T28, they cannot anyway be serialized. So the rest of T29 also does not come. So this is not a conflict serialization. Then if you draw the precedence graph, we will have an edge from T27 to T28 because read Q of 27 occurs before write Q of T28, and an edge from 28 to 27 because write Q of 28 occurs before the write Q of 27. Okay, so we can see that it will be having a cycle, and hence it is not a conflict serializable schedule. But if you see this example, what is the net effect? You see that here, who is doing the final write? T29, okay, and the value of Q that is written by T28, okay, in this example will be overridden by 27, which in turn will be overridden by 29. So if we had some serial schedule, say T27, T28, T29, okay, what would be the final value of Q? Whose write will be there? T29 will be there, okay, and what did T27 read? T27 read the value of Q, which was not written either by T28 or by T29. So if the original value of Q was 1000, Q read that, and then 27 might have changed 1000 to 2000, but 28 changed Q directly to say 3000, and 29 say changed Q to 5000. So net effect will be what? 27 will read the original value of Q, which is 1000, and final value of Q will be 5000 written by 29. So although it is not conflict serializable, but you see that its net effect will be similar to the net effect of a serial schedule T27, T28, T20. Are you able to follow? Okay. So this is what is called view serialization. Of course, this is not a conflict serializable schedule, but it is a view serialization. Now I will go back to the previous slide and say what is the definition of view equivalent. So remember previously we said a schedule S1 is conflict equivalent to a schedule S2. So I will just follow that particular slide. So you see this was our definition of conflict equivalent, whereby a series of swaps we could do. Now here what we are saying is that of course by those swaps you cannot make this equivalent to any serial schedule. Okay. So that means that this schedule is definitely not conflict serializable. But if, as I said, that its effect will be same as execution of T27 followed by T28 followed by T29. So this is an example which is not a conflict serializable schedule, but what we call as a view serializable schedule, and this is the definition of view serializable. So I went back to the previous slide. So if S and S prime are two schedules in the same set of transactions, of course, S and S prime are view equivalent if the following three conditions are met for each data item Q. So what are these? If in then in S prime also Pi must read the initial value of Q. If in schedule S, Pi executes read Q and that value was produced by transaction Tj, if any, it might be the original value, then in schedule S prime also the transaction Pi must read the value of Q that was produced by the same write Q operation of the transaction Tj. And finally, the transaction that performs the final write Q operation in schedule S must also perform the final write Q operation in schedule S prime. So, what of this, if you look at this example, that there is a read Q, and which value of Q is T27 reading? It is the original value of Q. Okay. So, now if I consider the serial schedule T27, T28, T29, so then in T20, in this schedule S prime, T27, T28, T29 means T27's read Q will be the first operation and which will read the original value of Q, which is also done in this, let us call this as S. Q of read Q of T27 is reading the original value of Q. So that point number 1 is satisfied. Point number 2 is not important because point number so no one is reading actually the value of Q produced by another transaction in this particular schedule S. So that's why it says if any. Okay. But the final one, you see that the transaction that performs the final write Q in S will also perform the final write Q in S prime. So here, who does the final write Q in S? It is T29, and if I have that serial schedule T27, T28, T29, and T29 will have the write Q, so that also is satisfied. So all the properties are satisfied, of which the second one does not exist in this example. But you could have a similar example here. So that would mean what? That would mean that this particular schedule, although it is not conflict serializable, it is view serializable. And it is very easy to understand that conflict serializable schedules will always be view serializable, but view serializable schedules like this need not be conflict serializable. But we might be okay with this. So every view serializable schedule is not, that is not conflict serializable, has blind. So if we have a schedule that is not conflict serializable but has a but is view serializable, it will have blind writes. If you see blind writes, why? Because you see that T28 and T29, they are not reading Q, they are simply writing Q. So that is what is called blind write. T27 is not doing a blind write, it is reading Q. Maybe based on that, it is determining what would be written as the new value of Q, that is the write of 27. But 28 and 29, they are doing this blind write. So this is the symptom of schedules which do blind writes or which are transactions that do blind writes and are not conflict serializable. They are typically cases which are likely to be this view serializable, because if T29 or T28 did some read queue, then you had a problem. So especially if T28 did a read queue, then it will not help, because that read queue will be either reading the old value, and then if you move T28 below T27, then that T28 will be reading the value written by T27. So because T28 is not going, let me repeat, if T20 had a read queue before write queue, then it will not be view serializable, because then this read queue of T20 in this will be the original value. But in the equivalent serial schedule, I am saying T28 will be following T27. So in that case, T28 will read the value of Q that is written by T27. So that is not going to let it remain as view serializable. So it is a telltale sign that schedule will be view serializable but not conflict serializable when it has got this types of blind writes. And mind it that we could have even not have T29 in this example. If you just consider T27 and T28, so you see that itself will not be a conflict serializable schedule, but a view serializable schedule. And in fact, that is what the example was actually also. Like this was an example. it is not conflict serial as well, but it is the same example as the one that we are talking about, and you see that this is view serials. Okay. Now the problem is that determining whether any schedule is view serial, that is a NP complete problem. Okay, so that's why that like for any given schedule, whether it is view serializable, determining that is not likely to be in polynomial time. Okay, all those T not equal to NPs. But so you are not likely to have an efficient algorithm in determining this. But there are certain practical algorithms that just take for certain sufficient conditions. Okay, so if those conditions are there, then in polynomial time we can figure out that it will be conflict serializable. But if the conditions are not there, still it might be viewed serializable, but those cannot be detected by algorithms that are efficient because the problem is early on. So we are not going into that what types of conditions to be checked and all that, but those are sufficient conditions. If they exist, then definitely the schedule is view serialized. So for this particular chapter, we focus on these sections. Okay? So let us take a short break and 5 to 10 minutes, and then so it is 11 by my watch. Let us meet at 11:20. Okay. So then I will move on to the next chapter, which is chapter 15, where we will talk about how we ensure that the schedules are generated by the DBMS, which are going to be conflict serializable or view serializable, and so on. So far, we have only discussed the definition of schedules and transactions, their properties, and those things. So, when we say a schedule is conflict serializable or not, how we can determine if a schedule is conflict serializable or not. But we will not work like that. We will ensure that the DBMS actually only lets those schedules to be generated which are either conflict serializable or view serializable, as we will see. So, what mechanism or protocol does it use to ensure that only such serializable schedules are getting generated? So, let us look at 11:20. What is your name? Yeah, so in one piece of paper you can write both the names because Okay, so those who are joining online, I have started. I have unmuted once again. So today we'll continue our discussion on concurrency control. So far we have talked about. Okay, let me remove my mask. Yeah. So far we talked about the properties of transactions, and there we said that this isolation property is very important because we would like to have concurrent execution. But the difficulty is that if we allow any form of arbitrarily intermingling of the instructions of various transactions in the process of allowing concurrency, there is a problem. We will not be able to maintain the consistency of the database. Okay? So, so in that sense, database provides the support for also ensuring consistency. But again, even after everything, if the programmer has written incorrect logic, then database will never be able to do anything unless we have all sorts of checks and balances. So we'll see a few ways of ensuring concurrency control. One of that is what is called lock-based protocols. So lock is which you have already studied in the context of operating systems. So lock is a mechanism to control concurrent access to a data item. So data items can be locked in two modes. One is what is called exclusive mode or called the X lock. Other is in the shared mode, which is called the shared lock or often called the read lock. Exclusive lock is also often called the write lock. So you lock a data item by making an instruction which is lock X or exclusive lock S or shared. And these requests are made to the concurrency control manager by the programmer. So do not take it literally that the programmer in the program will write all this. So this actually is part of your transaction execution environment. Whenever you are doing a select or update, automatically the lock requests go. So in your program you don't have to write as in that sense as a programmer you don't have to write. So transactions can proceed only after the request is granted. And lock compatibility is very easy to understand. That if two transactions both are only reading, so both of them are reading on the same data item Q, so these are all with respect to a particular data item. Okay. So if a transaction Q1 wants to read the data item, similarly T2 is also only reading Q or reading, it can write to other data items, but for Q it is only having read operation. Then P2 also can take shared lock on Q. Now these two shared locks, SNS, they are compatible. So that's why it's written as true, which is obvious that if Q1 has taken shared lock on Q, T2 can also be allowed to take shared lock on Q, and that is what is meant by compatibility, and in that sense that it is written as true. But if Q1 tries to write to Q and taken an exclusive lock on Q, then T2 should not be allowed to take even a shared lock, because if the shared lock and tries to read, but depending on whether Q1 is writing Q and whether Q1's written value of Q is to be read by Q, or the value of Q that was there before T1 wrote to it, that should be read by Q, there is a conflict. So we would not allow any form of shared and exclusive, or between exclusive, of course, we will not allow to become compatible. So that means it is very simple that a transaction may be granted a lock of an item if the requested lock is compatible with locks already held on that item by other transactions. So it is not only between two transactions, Q1 and Q2, there could be multiple transactions. But any number of transactions can hold shared locks on an item. But if any transaction holds an exclusive lock on the item, no other transaction will hold any lock, either shared or exclusive, on that item. If a lock cannot be granted, the requested transaction is made to wait till all incompatible locks held by other transactions have been released, and then only the lock is granted. But we will see that there could be possibilities of deadlock. So let us see this example. That I have a transaction performing locking. So T2, what it does is it locks A in shared mode, and then it reads A, then unlocks it. Then it takes shared lock on B, reads B, unlock B. Now it has got the values of A plus B, displays A plus B. So locking as a lock, as you see, is not sufficient to guarantee serialization, because between this unlocking of A and this reading of B or locking of B, other transactions might write the values of B also. Okay. Then this value of A reads the original one, and the value of B might read some change. Okay. So that might become wrong. So locking protocol is so what it is to tell us is that just because we are talking about locking does not mean that we can allow locking to happen in any particular any arbitrary order. So we have to ensure that only certain ordering of locking and unlocking is done, so that the generated schedules are serialized. And that is what is called a locking protocol, a set of rules followed by all transactions, which is to be followed by all transactions while requesting and releasing blocks. Locking protocols restrict the set of possible schedules. So if we did not have locking, then as you can understand, or if we did not have a locking protocol, then the transactions could lock and unlock in any order, and we have all possible combinations there. But if you only allow the locking and unlocking to happen following a protocol, then only a subset of those possible schedules only will be generated by the database management system. So let us take this example. So you see that it is again a simple thing that this P1 is reducing B by 50 and adding 50 to A, and P2 is reading A and B and displaying it. Now say this P1 is locking B in exclusive mode, okay, and so when it does that lock XB, what it is showing is that in the third column, the concurrency control manager is granting that out. So that also is shown. So when P1 requests exclusive lock on B, since nobody else is holding any kind of lock on B, so concurrency control manager is granting this exclusive lock on B to P1. So that is what that means. Okay. So then P1 reads B, then B is reduced, right? B is written and then unlocked. And then P2 does the lock is A, and concurrency control manager grants that. So P2 reads that value of A, unlocks A, then tries to lock B in shared mode, because P2 is only reading both, so it is taking shared mode. So concurrency control manager now grants shared lock on B to P2, and P2 reads it, displays it, and then P1 locks A in exclusive mode, that is granted, and then P1 reads on, it's the value of A, writes it, and then unlocks it. Okay. So if you see that, so there is all these locks are getting issued by the concurrency control manager, because there is no incompatibility of locks, and it is a locking protocol. But is it correct? You see, the problem is that this Q1 was supposed to reduce B by 50 and update A by 50, and P2 should display A plus B. So again, if we take the example of initial value of say B to be 1000 and A to be 2000, then P2 should always display 3000, right? If P2 is executed before P1 or after P1. But in this process, what it did was that it read the value of A, which is 2000, and it read the value of B, which was 950. So you see that it is displaying the value of A plus B as 2950. So you see that arbitrarily, if we allow these locks to be issued and released, then it may not necessarily guarantee serializability of the schedules. Okay. As you see that the schedule that has been generated is not serializable, because neither you can move this read B above of P2 above the write B of P1, nor you can move this read A of P2 below the write A of P1. Okay, so it is a locking mechanism, but it did not necessarily lead to serializable schedule generation. Are you able to follow that? So, what we need is that we need to follow a protocol, and the first one and very important one is what is called two-phase locking. Two-phase locking what we have is that we have a phase in which locks are granted to a transaction. So it keeps on acquiring locks on A, B, C, D, P, Q, whatever modes of locks, and whenever it is acquiring, only if there is no incompatible holding of the locks on those data items, it will be granted immediately. But once it has acquired all the locks and it has released even one lock, then it cannot reacquire any lock or acquire any lock also. So that means there is a phase in which, often called the growing phase or locking phase, in which the locks are actually acquired by a transaction on various data items. Then, when all of them have been acquired, and once it starts releasing the locks, we say that the shrinking phase or the unlocking phase has started for the transaction. And once that phase has started, it cannot acquire any further. So you cannot have a mix of locking and unlocking of data items. First you have to keep on acquiring them, and then once you start releasing the locks, you will only be releasing the locks and you cannot acquire any further lock. So that is what is called two-phase locking. First is the locking of the growing phase, the other is the unlocking of the shrinking phase. Okay. So if you look at this example, so P3, you see that unlocking is happening at the end. Okay. Similarly for P4, I have the locks and unlocking are happening at the end. I am not having unlock of B before locking of A. Okay. And in whatever mode it is. So that is what is called two-phase locking. So two-phase locking protocol ensures conflicts resolution. This is the important part. That you see that a database management system cannot let you generate arbitrary schedules of transactions, then detect whether it is conflict serializable by drawing the precedence graph and determining cycles and so on. Okay. What it will do is that it will enforce a protocol, in this case two-phase locking protocol, which will always generate only conflict serializable schedules. And 2PL or two-phase locking of 2PL ensures generation of conflict serializable schedules only. Okay. And by definition, as we said, conflict serializable schedules are also view serializable. As I said, there is a growing phase, there is a shrinking phase, and it ensures that there is conflict serializability. And the point in which any transaction has acquired all its locks means after that it will only be releasing lock, that is called its lock point. Okay. Now there is a transaction T1 which is acquiring locks, okay, and then at some point of time, say at T equal to say 10:30, it got its final lock. Now it will release, so 10:30 it is locked. Another transaction T2 in the same schedule was also acquiring locks. At 10:31 it completed acquiring all the locks. Now it can only release the locks. Another transaction got T. This is going to be conflict serializable, but conflict equivalent to which serial schedule? That serial schedule which is ordered in the order of the lock point. So if T3's lock point is at 10:28, T2's is at 10:31, T1's is 10:30, then the corresponding equivalent schedule will be T3, T1, T2. Okay. Is that clear? The concept of lock point. So we see this example that, of course, this is a schedule in which first A and B, so it is a partial schedule, everything has not been shown. Where we have P5 has locked A and then lock B, then it has unlocked A. So once it has unlocked, it cannot lock anything else. And because it has unlocked, now P6 can lock A in exclusive mode. It writes and unlocks. And then P7 again locks A in shared mode and then read it. So lock conversion, sometimes you see that you might wonder that how will a transaction know what type of lock to take? Because see, as I said, a transaction you are writing several SQL statements, right? Select, insert, update, delete, again select. So you can have any number of such SQL statements in your transaction. Okay? So when the first transaction is getting executed, sorry, not first transaction, first say SQL statement is getting executed for that transaction. It does not know what you have written after that. Okay, so it does not know what lock to take. So say for one particular table, it is doing select as the first statement. So you will take a shared lock, but later on, suppose it will also update the same thing. Then it will have to take exclusive lock, but when it took the shared lock, it didn't know that it has to take exclusive lock because that statement comes later. So what you can do is that you can do a lock conversion. First you take a shared lock, later on you convert it to exclusive lock. Okay? And while releasing, that can release a shared lock, can release an exclusive lock, or you can convert an exclusive lock to a shared lock. But it is once again that in the first place, once you have done the lock conversion, so in the first place you are doing the conversion, but once you start releasing the lock, it will be part of your second phase. Or how do you try to convert it back to lower level, then it is part of your shrinking. So this is a lock conversion. But if you see that it takes A1, A2 lock, all of them up to AN, and then finally it does a write A1. So it takes shared lock on A1, A2 up to AN. Then update A1 means that shared lock on A1 is converted into an exclusive lock on A1 because they should do this right away. And here it is only shared. So you see that this concurrency can occur because this display that it is doing, these are all based on the original values of A1. And if you see that its lock point is here, its lock point is after this. So that means it will be equivalent to a serial schedule of T9 followed by T8. Okay. It is not T8 followed by T9 because this A1, whatever is written, is not displayed by T9 in its A1 plus A. Okay. So we see that it is equivalent to a serial schedule, which is in the order of the lock point of these two transactions, which is T9 followed by T8. Now deadlocks can occur. So consider this schedule where B is being held in exclusive mode in T3 for writing, okay, and then T4 it is holding shared lock on A, and now it wants to lock B in shared lock. But the concurrency control manager will not run this lock. Why? Because T3 is still holding, right? So it does not get it. But in the meantime, so it is waiting here. But then T3 is proceeding, and then it wants exclusive lock on A, but T4 is holding shared lock on A. So this cannot be granted because this one is holding it, and this cannot be granted because this one is holding it. And as you know, in operating systems you have studied, there is a circular weight here, and that is resulting in the deadlock. So two-phase locking does not necessarily guarantee that because it is not violating two-phase locking. It is also in its going phase. It is also in its going phase. So it is not necessary that 2PL will result in deadlock-free schedules. It can result in deadlock. So how is it handled? Then the DBMS will have to determine that there are transactions which are not proceeding, and it can check that they are waiting in the circular mode. So then the DBMS will determine or pick up one of them for rollback. So it can pick up one which is waiting for the less amount of time or whatever, some protocol or algorithm to determine which one will be rolled. And once one is rolled back, this is rolled back, it will be releasing this shared lock it is holding on it. That is the meaning of rolling back of a transaction. It will release all its lock. So this is rolled back. This shared lock will be released, and it will be able to proceed because it will get this exclusive lock. Unless another transaction in between also was holding shared lock on A. Okay. Or if this is rolled back, then this will be unlocked. B will be lock of B, exclusive lock on B by T3 will be released. So it will now get this one and it will be able to proceed. Okay. Again, assuming that nobody else is holding it for any of this, but because this was holding the exclusive lock, so no other transaction can hold that. So two-phase locking does not ensure freedom from deadlocks, as I said. So of course there is a possibility of starvation. So if repeatedly one transaction is getting rolled back, so it can result in starvation. So you can design the standard ways deadlock handling strategies that we have studied. Similar strategies can also be used for handling deadlocks in various markets. So deadlocks are a necessary evil, as you can see. Now, cascading rollback is also possible under two-phase locking. To avoid this, follow a modified protocol which is called split two-phase logging or STPL, in which transaction must hold all its exclusive locks till it commits a record. So you do not release the locks. If you release the locks early and then you do not commit, then what will happen? That the other ones will also be able to will have to be rolled down. So in order to do that, what you do is that you hold all the exclusive blocks till it commits a record. After committing only you release the locks. So nobody else will be able to get it. So there is no question of cascading rollback. And if it is cascadeless, also it will be recovered as well. And there is another one which is R2PL or rigorous two-phase logging, in which all locks are held till commit or abort. The middle one is S2PL is only the exclusive locks are held till commit or abort, and here all locks are held till the commit or abort. And in that case, the advantage is that uh, the serializable order will be the order in which they have committed. So that is what is meant by this S2PL and R2PL. So I think we might drop here because we have discussed quite a few things and it will be too heavy. So in our next class on Monday, we will take up time studies. So actually we are going to discuss, this is slide number 14. So we are going to discuss some more such stuff. So about 12 watt, so which will cover on Monday for sure, next Monday. And then we'll move on to recovery of transactions. And I have the second like fourth quiz on next Tuesday. Okay. We'll announce the syllabus for that. In the following week, we'll cover recovery of transactions and a little bit from section from chapter 12. Okay. Only a few stories. So I think we'll stop here. If there is any question, I can answer. If there is no question, I am stopping the recording.